And yeah, as promised, there's going to be a talk by me. And just a word of warning, like I'm not a very good Haskell programmer, at least not yet. But so bear with me. I'm more of like a happy enthusiast. But anyway, so I was going to talk today about writing a type checker in Haskell. So today we're going to learn how to write like a really simple type checker for a really simple programming language. And yeah, just as a short introduction, my name is Christoffer, and I'm the organizer of the Stockholm Haskell Meetup group. I also, you can find me on Twitter, or X as it's called nowadays. And I'm also here as a part of functional software. So I'm also the co-founder of a company called Functional Software. We do consulting, recruiting, and we specialize in functional programming languages. So if you need functional programmers for your company, or if you want to work with functional programming, come talk to us. For a long time now, I've been interested in programming language theory. So, and I guess maybe some of you guys are as well. Otherwise, I am talking to the wrong crowd. But I mean, you are interested in Haskell, so I don't know. There seems to be some kind of correlation there. Anyways, just let's review some basic inference rules. This should look familiar to most of you. No, I'm kidding. But if you read papers about type checking, it often looks a little bit like this. So one of the goals for today is for me to sort of try to bring type checking a little bit more down to earth. Because, it can look scary. And this notation has a purpose as well. It's sort of like the first time you saw like a Java program, it probably also looked like, just weird hieroglyphs. It's just that, like, to me, there seems to be sort of like a chasm right now between material that's very, very basic and material that's very, very advanced, like PhD level, like papers and stuff about type checking. So kind of the goal today is to try to bridge this gap. So to make like programming language theory a little bit more accessible. And like I said, today we're going to talk about type checking. Just so we're clear, and this actually did help me a lot understand like how a type checker actually works under the hood. Type checking, if you think about the compiler, comes in like this phase, like somewhere down the middle. Like we have the first step is usually to translate source code to tokens, and then you get those tokens and you build an abstract syntax tree, and from the abstract syntax tree you derive type information and can check that the program is or whether the program is well typed or not. And then after that you have code generation, which generates machine code or byte code. Unless you're writing an interpreter, maybe it just runs whatever you wrote. And sometimes type information is used in this step as well. But to various degrees. Like you can use it to inform compiler optimizations, etc. that happen in the last step. But yeah, bear in mind that like our input will basically be the abstract syntax tree, and the output will be type information. So yeah, just to repeat a little bit what I said before, so the type checker basically takes terms that come in from the abstract syntax tree and translates that to types. So if a term is well typed, we return the type of that term, basically. And speaking like Haskell terms, speaking like in Haskell types, you can think of it as kind of like a function of terms to like maybe type. And the reason there's a maybe there is that like it might not always be well typed. And then like this would be a really simple example. A real life type checker would have information about like if something went wrong, like what was it that actually failed to type check, like where in the program did this happen, etc. But for the sake of this tutorial, we'll sort of skip that. Also, there's a difference between like type checking and type inference, which can be kind of confusing. And I'm also going to confuse them from time to time, probably. So if I use them like a bit interchangeably, you know why. And type checking is basically like given a target type, check that the term conforms to this type. Whereas type inference is more like given a term, try to deduce what type this term has. And our type checker will kind of like alternate between these two modes. And yeah, well, the language we'll be type checking is the typed lambda calculus, or TLC. So if you see the abbreviation TLC somewhere, you know what it is. And the original lambda calculus only contains functions of one argument. Like that's it. That's the whole thing. Yet it is Turing complete. It's interesting, right? Anyway, to like spice things up a little bit, we're going to add type annotations, Boolean logic, and integers, all in 20 minutes time. But the reason we want to add a bit more is like otherwise it's kind of hard to demonstrate different kinds of types and how typing can fail, etc. Let's see. Oh yeah. So like just to lay the groundwork, we'll start by defining a term type. And the term is basically represents a part of the abstract syntax tree. And to keep things even simpler, we'll start off by just defining integer literals, Boolean literals, and conditional expressions. So we'll start there, and then like we'll sort of build up the rest of the type checker. And we'll also define a type, which in our case has two different cases. So either it's an integer or it's a Boolean. And just to give you some like practical examples, like how this could look. The text in black is like our pseudocode, like sort of the code that the user would type in. And then the text in green is what that kind of term would be. So for example, if you type 5, that would be an integer literal. If you type true, that would be a Boolean literal. Then we have an example of a conditional expression, which is a bit more complex. You see, like, then we have a, I can step back. You can see here in the type definition that a conditional takes, consists of, well, it's a conditional, and then it has three terms. And the three terms are the initial, like, condition, which in this example is the Boolean literal true, and then it has like two separate body terms. And like you're probably familiar with this form already. Like if the condition is true, then you get back the first body. If it's false, you get back the second, etc. And finally, we have another example of like a conditional expression. And like the important part here is like the what kind of terms this will result in. Okay, so let's type check this thing. So we'll start with like the easiest case, literals, because basically it's just, okay, if you see an integer literal, we know it's an int. If we see a Boolean literal, we know it's a bool. Simple enough, right? Everyone is nodding for the people who can't see the room. But yeah, so that's it basically. That's the rule for literals. Conditions are a bit more complex because we had, as you remember, like we had those three terms that make up the conditional, and So to satisfy like the type checker, the first part needs to be a bool type. So as you can see here, we try to pattern match on. We have our. As I should mention that the function is called infer, because it starts by inferring types. Then it sort of alternates between checking, etc. So maybe I should have called it something else. But yeah, infer is the type checking function. But anyway, as you can see, to infer the type of or to check the type of a conditional, we first try to infer the type of that first term, which was like the conditional part, or the condition rather. And that needs to be a bool. So with pattern match on something like a tuple that starts with a bool, and if this failed, we will not get back, we'll get back nothing instead of just. So then we end up in the catch-all part down here. So, okay, so the first term needs to be a Boolean type, and then the second and third terms, like the T1 and T2 in the example, they also need to be the same type, because as you might know, like you can't switch types. I mean, if it's at least if it's like, if it's JavaScript or something, you can do anything. But like since we want this to be like statically typed, both conditional bodies need to have the same type. So that's the rule for conditional expressions. And as an example here, you can see that, okay, this would be an example of a well-typed conditional, where it's like, okay, the first part is a Boolean literal, and then we have like an integer literal and another integer literal. And this would be an example of a, like, where we can't deduce, like it's not well-typed, because in this case, the first body is an int literal, and then there's a bool literal in the second part, like in the second body. And that doesn't type check, because it needs to be the same type. Any questions so far?
Is there a reason why you don't have the actual literals in the constructors for the literals?
Okay. So the question was, is there a reason why we don't have the actual values in the constructors? Very good question. I should have mentioned that in the beginning. Like usually when you have a type checker, I mean, you would usually put the values there as well, like because you want to do something with this code. You want to, so like when you want to run this, you're not satisfied with knowing that, oh, I put the bool there. It's like, oh, was it true or false? Like, oh, I don't know. I just thought you cared about type checking. But so in a real example, we would actually put, like, we would save the actual value that the user typed here. But for the purpose of just type checking, we actually don't need that. Unless you're starting to talk about like dependent types, but that's like a whole semester at university, not like a 20-minute tutorial. But yeah, it's a good question. Okay. Any more questions so far? Okay, so now we start to get into a bit more like tricky or advanced stuff. Functions. And like you can see here, the parts I put here on the right is just pseudocode for like how a user might write a function in our make-believe language. And as I mentioned previously, like we're working with the lambda calculus here. So functions only have only accept one argument. So yeah, basically like the first form here is like, okay, this is how you define a function. This is also usually called like a lambda expression. And the important parts to note here is like, okay, we have an argument variable and a function body. So that's basically, this is a function definition. Then we have function application, which means given a function, apply it to the argument. And like, what actually happens under the hood, if you think about it, is like, okay, if I apply this function to the argument true, then everywhere an x occurs in the function body, replace x with true. That's basically what function application means. And if in the theory, this is called beta reduction, which means to basically run the functions. Sounds pretty obvious when you think about it, but there are some like the type checking makes you think about these kind of things in a kind of a different way. And also like, okay, so these are function expressions, but what is a function type? So a function type is also a bit special because it's actually a function of two types. So a function type is something that maps an input type to an output type. And if you remember the int and bool, like they're like, they're just int and bools. They don't contain any more types inside them, but function types do. Okay, but now we kind of run into a problem, because before we were working mainly with inference. Like if we saw a literal, like a bool literal, we knew it was a bool, etc. But how should we type check functions? So if we imagine that like type checking, like we said before, is a recursive function that takes the terms as inputs and gives the type as output, how should we type check this? So the problem is that like the funX thing, that's the first thing we get. Like inside is a term that we haven't type checked yet, but when we apply the function, we also want to know if it's like, if the application is well typed. But we don't know what X is supposed to be. Like intuitively, you and me, we can see that, well, of course, this is supposed to be a bool because there's a Boolean expression inside. But if you want to translate this to a mechanical algorithm, suddenly it's not so simple. You need some way to sort of understand that this is supposed to be a bool, like without like looking ahead. And one way to solve this is to simply say, well, no, let's look ahead. Let's try to be like a bit clever. And that's the basis of Hindley-Milner type inference. Basically, it says that, we don't know what X is yet, but that's fine. Like, we'll figure it out as we go along. So in Hindley-Milner, once you get in the function body, it would resolve this to a Boolean. Then it can, okay. And basically Hindley-Milner, like Haskell uses, is about building up like a network of constraints that sort of say like, well, and did we see this like X before anywhere in the program? Then we can go back and fill that in. And also then we can see like if there's a mismatch. But the Hindley-Milner is not like a silver bullet. It's really cool. It's very, it's very convenient. But it has a bunch of problems. First of all, it can be quite slow for large code bases. And also, we don't know where the mistake was. Like, did we use this function wrong somewhere? Or was the definition wrong from the beginning? Because this is like Hindley-Milner turns type checking into constraint satisfaction problem. We don't know which constraint was supposed to fail and which one was which one was the right one. Anyway, so there are other ways to solve this, but we'll settle for the simpler one today. I'll give you some pointers if you want to know more like advanced theory. So basically, we sort of like throw in the towel and add type annotations to our function. And that solves the problem of not knowing in advance like how X is supposed to be used. This also introduces the idea of a function scope or like a function context. Because basically what happens when you have a function type is that the argument and its type gets added to a context, which says that from now on, like whenever you see like X being mentioned, that has then X has this specific type. So bool in this example. And yeah, also we also save the we also define the output type of the function. So okay, how can we accommodate this in our type system? First of all, like I said, we need a function type. So we add a function constructor to our type. And as I said before, it has a function type is actually a mapping of one type to another. So we put two types in there. Also, we need to extend like the term type with a bunch of more constructs. So we've added lambdas, which is like a function definition. Variables, which is like any time you mention a variable, like X in the example here. And also function application, like when you run a function. So just to give you some more term examples, this is how a user might write a simple like identity function, but we don't support polymorphism, so this is only for like one integer to another. So what it does is like get an integer as input, and it returns the same integer. And that gets turned into like a term that looks like this. We also have lambda application, which is when you run a function. And here, like since application is on the right-hand side, it might be a bit hard to see here, but we define this function and then we immediately run it with 10 as the argument. And as the last example, you can see a bit more complex function that contains a conditional. Also, that context I mentioned needs to go into the infer function. So basically, you can think of the context as a mapping from names to types. So in Haskell, that would be typically like a map parameterized on string and type. And this sort of gives us almost for free the rules for type checking variables. Like anytime we see like an X being mentioned, if we knew that like in this context X is a bool type, then we know that, well, X is a bool type. So this is pretty easy. You just look up the name in the context, and if it's like an undefined variable, this will return nothing. But if it does find a type, it will return like just and the type. Okay, so this is one of the more complex type checking functions. How to type check a lambda. So we start by adding the variable to an updated context. And as you remember from the previous slide, context is a mapping from strings to types. So we start by adding the argument variable and its type. And we know the type already because, as you can see here, the lambda stores the input and output type in like the term, like its term type. So we know that the lambda always, like if you have a lambda, we know the input and the output type. So let's we start by inserting the input type in the context. And then we check that, then we run the inference function on the function body with the updated context. And if that still makes sense, using the variable rule that we introduced before, then we get back a type. And we expect that type to be the same type as the function's output type. So basically, take the function body, check that it's the same type as we said that the output or the output type of the function. And if we succeed, then the type of the function or the function expression is a function type with the given inputs and output types. Otherwise, it's nothing, and we fail to type check. So yeah, some examples here. For example, So if we have a lambda and we say that let's say it's a type from int to int, and the variable name is x. Yes?
I have a maybe silly question, but what happens when you sort of self-reference a function?
Oh, that's a very good question. So the question is, like, what happens when you have a function that refers to itself? This type system doesn't support that. And also, it's very, very good, whole area of programming language research. But the annoying thing is, like, this type system does not allow for recursive functions. Otherwise, you need to sort of do a little trick where you say that, like, I'm going to put a placeholder type in here. So let's say we have two functions that call each other recursively, A and B. So what you do is, like, you put in a placeholder type for one of the functions first, and then you type check the second function, and then you can go back and check the first function again. Like, does do the type definitions match up? And it's, I mean, it is tricky, but the interesting thing is that if you don't add this, you have a programming language that never crashes, basically. Because if you think about it, like, it's what you call a total functional programming language. Because let's say you don't have any side effects in your language. Basically, the only thing that you can go wrong, like, and all operations are defined. Basically, the only thing that can go wrong is that you fall into an infinite loop. But without recursion, that can't happen. So yeah, you can look up total functional programming languages after this, because it's a very, like, interesting and promising area of research, I think.
I mean, if you don't have types, then you can circumvent that by just defining the Y combinator.
Exactly. So if you don't have if you don't have type checking, you can sort of sneak in recursion. So you're only safe if it type checks. Otherwise, you can put in an Y combinator, and then all of a sudden you run into an infinite loop, and you get non-determinism, and everyone is sad. And
But more specifically for this language, since we have the output type, we could just operate on the presumption that that's correct the second time we see the function, and then if it type checks the first time, it should be valid still. So
yes.
we could support it with some additional.
Yeah. So what you do basically in a type system is that you introduce something called a fixed point combinator.
No, I mean, for this specific problem of self-reference here, we could type check it by just assuming the output type is correct the second time we see that we're trying to type check the same function.
Yes, but you can't complete type checking the function if it.
You just assume it's the second time you see it, you assume it's the output type, and then you complete type checking the first time, and then if it's it should always do.
I mean, there's no mechanism for self-reference in the language to start with.
No, of course not. But
yeah, and I guess I'm not so, like I said, I'm not so good at this stuff. But I think that's sort of how the fixed point operator, or like the fixed point construct works. That you sort of say that, okay, I mean, we just assume that it does work like this, and then we proceed with the checking. Okay, we're almost there. So hang on, hang tight. And sorry, any more questions about the function definition thing? So this is actually the final rule. So the one thing we have left is function application, as in like running a function. And so the first thing we need to do is, as you remember, sorry, let's just jump back and remind ourselves what it looked like. Function application is a term that has two terms inside it, basically. And so you can think of the first one as the function and the second one as the argument. So to check application, the first thing we need to do is to make sure that the first term is indeed a function. So that's what happens here. We check that, okay, is it a function? Because only functions are valid in that like application position. And if indeed it was a function, we also like grab its input and output types, which we know are correct by now. This is important to keep in mind, and when it's good to have a proof assistant handy, because this you sort of have to track a little bit in your head, that we already checked that the function is well typed by this point. So we know the input and output arguments. So the only thing we need to do now is to check that the argument that we used in the application is actually of the same type as the input. And if that type checks, the type of the entire expression is the function's output type. And yeah, again, some examples here. So like a well-typed application, for example, is like, okay, we have a lambda function and we know it's like an integer to integer function. And this was the identity function that we saw before. We just return whatever the user put in. And then we saw that someone put in an integer literal there. And then we know, oh, okay, that's the same type as the function's input type. And then this will evaluate to just int, because that was the output type of the function. And this is something that doesn't type check. For example, we take the same function, we use a Boolean literal here instead. And then that does not match the input type of the function. So then we fail. We say, oh, that doesn't work out. And that's it. I counted the lines in my editor. I think it adds up to like 40 lines or something, which is not that much, but like it feels like there's a whole lot of power in this like really simple algorithm. And now you can type check the Boolean, or sorry, the lambda calculus with Booleans and integers. Any more questions? Oh, I'll try to put up the slides and a video, etc., on the meetup group somewhere where you can find them easily.
Possibly a small question.
Yeah.
We had the type annotation for the output type of the function. The only thing it was used for was verifying that the inferred type was correct. So why isn't more languages inferring the output type? I guess is what I'm sort of getting at. It seems so simple. Just not include that annotation.
Yeah. It's more of a like. I'll show you a trick. No, remember, and this is now we're getting into something that's like extracurricular reading, but recall that or learn very quickly that. So the question was like, why can't we just like why don't we just assume that the body of the function is well typed? Because then we don't need to like have a type annotation for the output. And I mean that's perfectly viable. It's more like in this case, it's more like the fact that how can I say? It's a bit annoying to have another function type where there is no output. Like so that would mean like you can have terms, but the thing is you don't need either of those things, and you can do it without Hindley-Milner with one simple trick, one weird trick. And like so, recall that when we were defining functions, we sort of do it the other way around, right? Like previously, we were sort of inferring types. We were looking at the literal, and we see a literal, we know, oh, it's a bool or an integer or whatever. But with functions, we start by, let's see if I can find a good one. Yeah, we do it the other way around. Like we start by saying what the types are supposed to be. But what if the function is in a place, or rather, or more like this, what if the function is an argument to a function that already, like, that expects a function that has a given type? So, and this happens quite common in functional programming, right? Like you do like a mapping over a list, and then you type out the lambda function, and you know in advance what the type of the list is. So in that case, you don't need to add the annotation. You know what the input type is supposed to be. Because I know I'm working on a list of integers, for example, then the only type that's valid is would be integer. So then instead of like jumping over and saying like, oh, now we need to type check this, you just keep type checking the function body instead. So you have the compile or the type checker substitute this with integer, so you don't have to type it yourself. And then you can see, oh, does the body still type check? In that case, like, yay, it's well typed. So yeah, that doesn't work for everything, but like, you know, and also for the body you can use the same trick that you mentioned, like just check what the return type is supposed to be. And actually, there is what inspired me to write this was this tutorial by David Christensen, and a lot of the code samples are kind of adapted from that. And this actually goes through a technique that's called bidirectional type checking for doing this without the inference. And also, if you thought this sounded interesting and you want to learn about the other parts of the compiler chain, you can read Crafting Interpreters by Bob Nystrom, which is free to read online. There's also a really good, if you actually want to learn those weird symbols we saw in the beginning, you can read a post called How Should I Read Type System Notation on Stack Exchange, which actually has a really good guide for like how to learn that annotation, or learn that notation, I mean. If you want to learn more about like Hindley-Milner type inference, there's a freely available course online from Cornell University where they take you from scratch to like working ML-style interpreter. Yeah, that's it.